Alright, so where the fuck was that? So we're solving the so-called simple pendulum numerically, which is a second order differential equation. And let's take a quick inventory of what we have. We have our system of two differential equations being numerically evaluated using Euler's method as such. Then we reduce the initial angle then over here we have the so-called small angle approximation, and we note that it's mostly correct except in cases where the angle is not small. So because this is ultimately game dev shit, I went ahead and introduced a bunch of keyboard controls to the main loop. So now we can start interacting with the pendulum. So let's begin by commenting out this bullshit. And my thinking here is this is gonna be something of a grappling hook rope swing, where the length of the rope can change during gameplay. And so you'd think the only thing you have to change is the length of this. So let's try that. Press up, our length decreases by some number, and if we press down it increases. And we see that the change took. So if you ever took like a fucking yo-yo or whatever the fuck and spun it really fast with a long string, preferably around a bunch of people, you'll notice that if you grab the string somewhere in the middle, the angular velocity should abruptly increase. Like this should be spinning all over the place, and this should be spinning very slowly, the long rope. But that's not what's happening here. And the reason this is happening is because this differential equation, you notice the variable L. Now variable L here is assumed as a constant. Therefore, the equation or the system knows nothing about L if it were to vary in time. So what the fuck do we do? Well, because this is a computer science lecture and not a physics lecture, I'm not gonna show you how to actually solve it. You know, take the Lagrangian and so on and all that bullshit. I'll just show you the final solution, which is just this. So all we have to do is numerically solve this new equation. And there's two things we notice about it. Number one, along with the second order derivative term, we now also have a first order derivative term, as well as the non-derivative term. So it feels like a more complete non-homoerotic or whatever equation. Secondly, we notice that this first order derivative is usually associated with damping or attenuation in these kinds of second order systems. So naturally we infer that the change of length, which is literally represented by derivative of length over time, will affect theta in some manner. So, and then thirdly, fuck it, yeah. Anyways, so the first thing we'll notice if we isolate the second order derivative, these terms simply, so this becomes minus 2 over L times derivative of L times derivative of theta, which we define to be A2. Right, so A2 is d theta over dt, and we already have it as A2. And so then we take inventory, or what are our knowns and what are our unknowns. Because we're directly changing L, we always know L of t, and by always knowing L of t, we always know dl over dt. So and of course, if dl over dt is 0, meaning there's no rate of change, this entire thing becomes 0, and you collapse back into this equation. So all we have to do is, we've written out the equation here. All we have to do is that when there is a change in length, there is also a change in the rate of change of length, which we represent by dl. So then dl here, dl being a derivative, which is nothing more than a slope, is just rise over run. So our rise is 10, and our run is h. Of course, we'll repeat it here. So now, let's just see what happens. So if I increase the length, I should have this very slowing the fuck. Oh, okay. And because these rates of changes are abrupt, when you no longer press the keyboard, the rate of change goes back down to 0. So this should be nice. So of course we lose a little height when we increase the length. And now if very abruptly we say, as I've said earlier, grab in the middle, it should just start fucking, yeah, doing that. So you go in and you spin, or I don't know, spin around, and then so yeah, that's that. So that covers the up and down arrow keys. But we also happen to have left and right. So with left and right, I think it would be sensible to make them such that they simply increase velocity or acceleration. So left is minus. And our derivative of a1 is a2, of course. And this just becomes, again, rise over run. So let's start with an initial condition of 0. Fuck. So that was me pressing the left and then pressing the right. So here I am, I don't know, trying to swing. So let's do like a typical gamey maneuver. So we're at this length and we're trying to swing our way up. Yeah, fuck it, let's call it there.